In this video, we're going to focus on finding a Norton equivalent for a general circuit. No limitation on the circuit other than it's got to be a resistive circuit, because that's what we're talking about here, and a linear system. But you can have any component, dependent, independent source, resistors in there that you would like. Here's a simple one that's got a little bit of everything in it. The process for finding Norton equivalent is very, very similar to what we did for Thevenin equivalent. It just in the end we draw a different model, and as a matter of fact we could have drawn either model, and we'll show that here as we go forward. Here's a simple circuit put together. So as we had discussed before, step one when you're doing a Thevenin equivalent is that for step one we need to leave the point where we want to find a Thevenin equivalent. In this case, we want to find a Thevenin equivalent with respect to A to B. So step by, we'll just have open the two terminals A and B, and then we will try to find the voltage across A and B, which we're going to call V Thevenin. So V Thevenin is going to be V across A and B when there's nothing across it. Now, when we say nothing, we're not talking about cutting the elements that's part of the circuit. We're talking about not adding load from external when we're doing the Thevenin equivalent, because Norton equivalent or Thevenin equivalent, because this equivalent is supposed to be for the circuit excluding load and external stuff. Okay, so in order to do that, all we have to do is basically take the circuit and solve it either with KCl, KVL, or one of the other analysis tools that we have learned so far. So what we say, okay, the easiest one for us to do here is a KCL, or the node voltage method. We're going to call one of the nodes V reference, and then we'll name this one V1, and we'll name this node V2, and that's all the nodes. Actually, that's not even in a sense, actually, to be exact, this is not an essential node, so we can actually literally leave it alone, or you can include it. In this case, it's a little bit convenient to include it, but let's say it's only one place, one essential node, which is so we do a KCl at V1, and if we do that, we're going to have V1 minus 10 divided by 10, and I'm going to use volt, kilo ohms, and milliamp. This way I don't have to carry a lot of zeros with me, plus V1 divided by 10 plus 0.5 Ix equal to 0. And then we notice that this is a dependent source, so we have to write a dependent source equation. And a dependent source equation would be relating Ix to V1 or V2 or something. So in this particular case, we see that we can go ahead and write Ix, because we know the current this way is V1 minus 10 divided by 10. So all we have to do is put a minus in front of it, and we got our solution. Okay. We really are interested in the thing that is in here. So we can literally call this V2, even though we normally don't do that. We normally, with KCl, we only write the essential nodes, but this one is, is not an essential node, but it's very useful because we're looking for V2, and that allows us to quickly find V2 once we have V1. So we could do a KCl, add a V2 for this purpose, and will be V2 minus V1 over 2 plus V2 minus 0 divided by 8 equal to 0. So once we solve this, we can find, there's V1, V2, Ix, and we got three equations. Simply solve it using your favorite tool, and you'll find out that V2 is equal to 8 over 3 volts. Then we're going to leave that at this point. So that basically becomes, if you look at it, B is, we assumed is 0, so AB, this V2 becomes the same as VAB, which is what we were looking for, which was V Thevenin. So we found V Thevenin here. So now we're going to go ahead and try to go to the next step. So step one was this, and much like we did before, the step two is going to be, let's short across A and B, the terminals we are interested in, and then try to find I short circuit. So what we're going to do, we're going to put a short across here, and what we are interested in is this I short circuit. Of course, when we put a short circuit across here, this goes away, right? All the current will flow through the short we just added. And then, so since we've been doing KCL over there, let's go ahead and do KVL here, or the mesh current. So let's call this one I1. Let's go ahead and call this one I2. So if you go ahead and write the equation for it, you're going to have a KVL at I1. You can't do that because the shared node is a current source, so you're really going to have to do a super mesh at I1 and I2, which basically means when you write the equation, you got to go around both of those loops like that. And if you do that, we're going to end up with an equation which is minus 10 plus, again, for this also, we're going to use kilo ohm milliamp. This way we don't have to carry a lot of zeros. 10 I1 plus 2 I2 equal to 0. So that's one of the equations we get. Since this is a super mesh, we're going to write a super mesh equation which says I1 minus I2. So it gives us I1 minus I2 is equal to 0.5 Ix, which takes care of this. Takes care of the two equations we need for the I1 and I2, but then we introduce this Ix, which is a dependent source, so we really need to look around and write the dependent source equation, which its job is to relate the variable from dependent source to one of the I1, I2, and in this case we look at this thing and say, oh, Ix is simply I1, great. So again, you have three equations, three unknown, and I short circuit we know is equal to I2. So once we solve that, find I2, we know I short circuit is, which is going to be 5/11 milliamp, and we're good to go. So now we have the short circuit. So now we got to go to step 3. Step 3 is relatively simple. L and Mrs. R Thevenin is equal to V open circuit over I short circuit. Earlier we found that V open circuit, another name for V Thevenin, right? So there are many names for this one, but V Thevenin over I short circuit, and it's 8/3 divided by 5/11. We know that the current was in milliamps when we found it, and then the volt is volt. That means the resulting, whatever the result is, going to be in kilo ohm. And if my calculation is correct, this should be 5.9 kilo. Finally, in step 4, we do the Norton equivalent, right? And the Norton equivalent simply is going to be a current source and a resistor. So this is A and B. So the circuit above can be replaced by this circuit, which has our Thevenin of 5.9K, and I short circuit or I Norton of 5/11 milliamp. You can do this, or you can convert, or you can basically do a source transformation. If they were asking for Thevenin, this was not asked for, but just to be, if they asked for Thevenin equivalent, we have all the information we need to do that. So doing a Thevenin equivalent and Norton equivalent, the process is exactly the same. The only thing that changes is which one of these models do you draw that in. And of course, this would be V open circuit or V Thevenin, which is 1/3 of a volt. Okay, so that's basically how we go about solving a general case where for almost any circuit, you just say, okay, first thing I'm going to do, I'm going to not connect anything to A and B, leave it open, and and then find V Thevenin. And now we know this is sometimes also referred to as V open circuits, not to confuse things. You solve that, you find V Thevenin, then again you solve this equation. This time you put a short across it, and this would be your step number 2, short circuit, and you find I short circuit, which is the short circuit is between A and B. And from there we find I short circuit, use that to draw either a Norton equivalent model or a Thevenin equivalent model, which is shown below.